Okay, let's get started. So today's topic is to prove undecidability using Turing reduction. So what is Turing reduction? We use this symbol, the less than and equal and a t to express Turing reduction. And what's on the left is a language that is easier to decide. We denote it as LEC. And then we have the language that is harder to decide. So the definition of Turing reduction is that if we have a decider for the L hard, then we can construct a decider for the LEC based on this decider. So it typically means that this language is easier to decide than this language. So how do we prove undecidability with it? We typically choose this language as the language that we need to prove, and this language to be an undecidable language that we have already proven undecidable, such as L hot, L bubble, and L accept. So let's see what steps we need to prove this undecidability. So first step is that we need to declare a membership oracle for the L hard. So we need to declare this is also called a black box. This means that we assume there is a decider that can decide the L hard language. And then we need to construct a decider D for the LEC language. Based on the oracle we have declared. And the final step is that we need to prove that our decider correctly decide the language. So let's look at an example. We need to prove that L quick hot is undecidable. What does L quick hot mean? It means we're taking a Turing machine and the machine can halt on some input X within the length of X steps. So how do we do that? First, we need to find a Turing reduction relation. So we write this symbol here, and to the right, we need to just plug in the language that we need to prove. This serves as a harder language. And to the left, we need to find a language that is undecidable, and we have learned it, and it has got similar property with the L quick hot. So we think about L hot. So let's quickly recap what L hot means. It takes a tuple of a Turing machine and an input, and it means that M will hot on X. That's its definition. So intuitively, those two languages are not equivalent because we can construct some language that lets the Turing machine suppose for all the x, this machine has on x at exactly x+1 step. So let's investigate this language. So does this machine, is this machine in the LP hot? It is not, because for all the x, it has more than x steps, so it does not satisfy this qualification. But because for all x I'm always hot, it is actually in L hot. So we cannot just declare that these two languages are equivalent. So what do? We notice that the basic contradiction is at here, because the number of steps is constrained by the input x. If we can let it be an arbitrary number for some n, for example, then we can find that actually if m hot, it is totally equivalent to if m hot within n steps for some n. So how can we achieve this? We have got two strategies. The first one is that we always construct a new language m prime that is different based on the original Turing machine that we input, and it differs in the input argument. And the second strategy is that we always let the Turing machine m prime to ignore its own parameter, its own input, and run m on x, where x is the Turing machine m's input. So how can this work out for our problem? So let's write the solution and just get our goal. So first step, we declare a member oracle for L hat. So we write let O be a membership oracle for L hot. Wait, sorry. You need to notice that we need a membership oracle for L hat, which L hat here means L quick hot. So the next step, we need to construct an m prime based on m, and let m prime to run m on x and ignore its own input. We denote its parameter or input as w. And what does it output? If you cannot figure out immediately, you can just say output whatever it outputs. If you find a conflict in the future, then you can always go back and revise this. Then we need to construct our decider based on our oracle. For our L easy, which in this case is L hot. So what do? We always call the oracle, and we do not call it using the parameter m, but m prime. This is why we construct m prime. And what does it output? If you cannot figure it out immediately, then you always just write output whatever it outputs. So we have actually already done at least from our steps. And now we need to do the third step, that is analysis. And whenever we find something wrong here, we can always revise the previous steps. So we need to prove that our decider actually decides L hot. So there are two situations. One is that the input X belongs to L hot. What can we imply from here? It simply means that, because L hot actually takes a tuple of a Turing machine and an input. This means that M hot on X. And what's next? So if we want to build some connection between the M and M prime, then we need to write something that concerns M prime. Let's see what M prime does here. Because M hot on X and M prime is defined as ignore its own parameter run M on X. So actually M prime also hot. And this is now the tricky part. What does the M prime hot infect the behavior of the oracle? So the oracle is defined as this quick hot. So if M hot on some input X within X steps, then the oracle will return accept. So is it this case here? So we can notice that actually M prime takes W as an input, which is not X here anymore. So actually we can regard the length of the W as the N here. It can be an arbitrarily large and a finite number. And so it always hots on some input W within the length of W steps. And because M prime always run M on X, X is not relevant to this. So we can conclude that the oracle that runs on M will accept. And because from this line we output whatever the oracle output, so the decider actually accepts M. So we prove that whenever X is in L hot, then the decider will accept, this is also a tuple, accept the tuple of M and X. And similarly, we can write the Mx not in L hot situation. We basically negate all the steps here. This is also a tricky part. How do you transfer from this statement to that O m prime rejects. Because m prime does not halt, we can see here that for all the input W that is passed into the m prime, because m prime always not halt, because m does not halt on x, we can conclude that there is no W that within the length of W steps the machine halts. Then we conclude that our decider rejects its input. Okay, so now we can see that after we have adopted the two strategies, we just fluently figure out that we have already done the process. And finally, we need to conclude. Therefore, this is also very important in your exam. You need to just write down all the finishing stuff. So here we say that D is a decider for L hot. This concludes that L hot can be Turing reducible to L quick hot. And therefore, because L hot is not decidable, L quick hot is also not decidable. So you can see that the most important process of this problem is that you need to first know what steps we need to take to prove the algorithm, prove the undecidability. So the first one is that we declare a membership, and for the L hot, and the second process is that we construct a decider for the L easy. And third, we prove that our decider correctly decides L easy. And the two important strategies that works 99% of the time in exam are these two, which is construct a m prime based on m and it differs in the input argument. And secondly, we need to let m prime to ignore its own input and run m on x. That's it. Any question?